Hi there, everyone. Thanks for joining in for this online version of SWE 432's deployment lecture. My apologies once again that I had to leave town unexpectedly due to a personal matter that just came up. So in this lecture, we're going to be covering maybe some more big picture topics. Uh, so far, we've talked about how we can build apps technically, very technically. We talked about JavaScript stuff, we talked about React, we've talked about HTML and CSS. Today we're going to talk about more process-oriented stuff. So if we're going to go out and maybe start a company or join some company that's going to be like in the business of making apps and web apps, the question is going to arise of how we should structure the process, like the business process, the human process that we take in order to ensure that we're going to end up with the great products that we would like to end up developing. This will be a pretty big buzzword lecture in terms of talking about topics that are maybe pretty hot. We're going to talk about topics like DevOps and continuous integration, continuous deployment, continuous delivery, and a little bit of, as usual, the historical aspect of how we've got in to have these processes. We're not going to talk about technologies. If you find this stuff to be interesting, I've got a link on the slide here to a great blog post and some videos. It's a little bit dated, but still pretty relevant, I think, from Chuck Rossi, who's a release engineer, release manager at Facebook, that describes their development and release process. So before we get into deployment and this big picture stuff, let's just remember what we covered on Monday. So Monday we were talking about security. We talked about topics like the different kinds of security requirements that our apps might have. And we talked about 4 high-level requirements, which were authentication, authorization, confidentiality, and integrity. So recall that authentication versus authorization. Authentication means that we verify that someone is who they say they are. That's maybe checking a driver's license and verifying that photo ID matches that person, checking a password. Versus authorization, which was once we understand who someone is, should we give them access to some resource? And then confidentiality and integrity were requirements that we applied to data. So we want to make sure that information was only being given to the correct authenticated parties and that that information is not being changed or tampered with, and it's being transferred securely. We talked about threat models and how at the end of the day you have to identify what it is that you need to defend and what it is that you're going to trust. In terms of what it is you're going to defend, we talked about identifying different kinds of resources that might be important to defend. In the context of our meme system, that might be as simple as just protecting the email addresses and passwords if we let users sign up for our system. And then also considering what kinds of malicious actors there might be, those black hats, the bad people, and the different kinds of attacks that they might employ. And that this is going to vary a little bit based on the value of the information that we're trying to protect. So if we were protecting just like information about some memes that someone was generating, I don't know that anyone's going to risk like hundreds of millions of dollars to steal that data from you. But if we were, say, Equifax and we were storing the financial information for every American individual, certainly it could be worthwhile for someone to spend hundreds of millions of dollars to break into your system and steal stuff, in which case you might be more motivated in trying to defend it. And on the trust side, we said that something always has to be trusted within our system. Maybe we'll trust ourselves that our code doesn't have bugs in it. Maybe we'll trust the computer that is running our code that it will faithfully run that code. Maybe we're using frameworks and libraries and we trust that those frameworks and libraries are correct. One kind of threat that we talked about was this man-in-the-middle attack, where that black hat evil attacker might be able to intercept and tamper with all of the messages that are being sent between the client and the server. Kind of begging this question of, does the client really trust that the response they're seeing came from the server? And the server asking, did this request really come from the user? And we talked about the simplest way to avoid these man-in-the-middle attacks was simply using SSL, using HTTPS. And the last big topic that we talked about in Monday's lecture was this OAuth protocol, which was the protocol to allow us to have these consumer applications. The example that we used was a to-dos application, accessing some bigger service, a service provider like Google Calendar. And we wanted some way that this to-dos application could post events onto the user's calendar, but without the to-dos application ever finding out the user's email or password when it came to Google. So we said that OAuth was this conversation-style protocol where a user says to the to-dos app, hey, I'd like to be sharing my data with Google Calendar. Then the to-dos app says to Google Calendar, hey, the user said they'd like to do this. Google Calendar says, all right, let me check and see if the user really wants this. And then this redirects the user so that instead they get sent to a Google page. This is then when the user logs in and can say, yes, I'd like to authorize this application, have access to my data. And then Google Calendar or the service provider will generate this special token. And it's going to send that token back to our consumer application. And then that token is going to be how our consumer application can access that resource, because whenever the consumer application wants to talk to Google Calendar, the service provider, it can send this token and the service provider can verify, yes, I sent you this token before, you are who I think you are, everything is good, I'll give you access. So just a reminder, as I posted on Piazza, because of my absence today and also on Monday morning before the exam, this topic will not be on the midterm, and today's material will also not be on the midterm. Okay, so let's get into today's topic. So we're talking about deployment and software processes. So this begs the question, what is a software process? So formally, software process is a structured set of activities that we take as developers to develop a product. And the process generally involves at least, well, at a high level, maybe we'll just say just these four high-level tasks, which is going to be specification. So this is when we set out maybe with our business folks who say, we've got this idea for this great new product. I've got some new software. It's time to build this, and here are all the features it should have. So specification is going to be the phase where we're deciding on what features we're going to use and how they're going to interact with each other maybe. Then we always have a design and implementation phase. So this is translating these business requirements into maybe what's going to end up looking like code, or designing APIs and implementing all of that stuff. Then we validate this. So this is taking the code that we built and bringing that back to the users, bringing that back to our customers, and seeing, does this meet those needs? Finally, there's going to be an operation and maintenance phase where we have our software and it's running and it's being used, and we might need to fix bugs or add features, evolution. So this is maybe a model for how you could develop software. And even if you're not formally doing any sort of process, when you build software, you're probably doing all four of these steps. Hopefully at least the specification and design and implementation phase, and certainly the validation one. So the idea of turning this whole thing into a formal process is to try to minimize risk. And risk in software process might mean things like falling behind on schedule. So if we say that we'd like to have our product released, say, in 6 months, we'd probably like to make sure that we can actually meet that goal rather than just pulling 6 months out of a hat and saying, ooh, I don't know if we're going to make it or not. We also want to try to minimize later changes to the end user requirements that could come in and subvert the development that we've already done. If a user comes back to you in the middle of your development cycle and you've already spent 6 months building some app, and they say, oh, actually, we don't really see this as an app. We see this as a mobile lifestyle experience, or I don't know, some like absolute craziness here. This could totally change what it is that you've done and make you have to throw away what you've worked on, and this can be a large risk in terms of falling behind schedule and maybe things becoming too costly. And lastly, we want to try to minimize the risk of introducing bugs. So it turns out people have extensively studied software processes and how they're used in practice. And there's data that shows that, well, if you try to design and build your software in this way instead of another way, you might be less likely to introduce bugs and therefore eventually end up with correct software faster and cheaper. So let's go step through step here. We've got specification, design and implementation, validation, and evolution. So what does the specification phase entail? Specification is this process of establishing the features and services that are going to be required, plus different constraints on the system's operation and development. So in the context of our meme system, I've got meme base. We can come up with specifications in the form of requirements. If we were really building the system in a large scale, we might go through a formal requirements engineering process, doing things like feasibility studies, where we try to understand the existing market and the features that are needed, requirements elicitation analysis, where we find all of the stakeholders, anyone who might be using the system or a customer of the system, and find out what they want. Then formally specify those desires into specifications, and then eventually validate that those requirements are what we implemented. But anyway, in the context of the meme base, we're going to end up coming up with some requirements, and they might be as simple as users can make memes. And then this requirement might have subcomponents like choosing a template or not. We have this template thing. Maybe we have users can generate meme templates. And then each one of these might have some sub-bullets like what does a meme consist of? Consists of a template, plus some customized text, and a template might consist of an image and some text blocks or areas. So these requirements are at this level of business use cases, right? We're not saying anything about React, we're not saying anything about components, we're not saying anything about Firebase, we're not saying anything about JavaScript. This is just purely business requirements. So the business requirements for the meme base are that users can generate memes, and a meme is a meme template with some customized text, and users can create meme templates. And a template is image and text areas. And we could add, more detailed requirements like generating a meme from a template increments a count or something. And just keep going on in detail. And if this were a class in requirements engineering, we'd probably make a big deal about this and have a much broader list than this. But let's keep it moving on to the next phase. Hopefully we understand the key concept here. So the next phase is going to be software design and implementation. So this is where we're going to take these requirements, this system specification, and we're going to convert this into an executable system. So we've got our requirements, and now we'll actually build it. So we define this design and implementation. These are two very tightly coupled phases. The first is going to be design. So this is where we're going to design the software structure to realize this spec. So what might our design entail for the meme base? Well, we're going to have to answer all different kinds of technical questions, right? Like, where is data stored? What is the data format? What language should we use? And frameworks. If we decide, for instance, that we're going to be using React, then we might want to start including some React-specific design in here. So like components, what are those components going to be? This design phase could also include more usability kind of design, which is something that we'll focus on starting after the midterm. So the result of this design process is going to be some documents. Look, it's a file. Shading. Some documents that describe maybe UML diagrams. I think probably in some class we forced you to do that. That describe what the system is going to look like, and then we're going to take that and we're going to take those documents and actually turn these into like, some executable code. Implementation is maybe what we're most used to focusing on, which is going to be taking that structure, turning it into an executable program. Design and implementation, we put them together because they end up working very closely together and might happen to be interleaved. Then we had validation. So validation and verification are intended to show that now that we've got this implemented system here, this thing, we want to show that it actually conforms to the specification, like if we zoomed out, right? Like our customers came up with this list of requirements. Right? This all is from the customers, and this all is from us. So verification validation is where we're going to take the artifact that we've produced here and go back to the customers and make sure that this is going to actually implement the requirements that are laid out there. This might involve checking or testing kinds of work, where we might look and see that, like write tests to see that requirements are implemented. It might also include formal verification, which is pretty far outside of the scope of what we're going to talk about in this class, or probably in almost any undergraduate degree, but it turns out that there are ways where you can actually logically prove that a system is correct to some specification. In terms of how this verification validation occurs, we might do this with acceptance testing, which is where we'll be executing the system that we built with some test cases derived from what the customer tells us they'd like, or more increasingly beta testing, where we actually just take the system and throw it out in production and see what actually happens. This is maybe what we're more used to seeing in a web kind of environment. We'll see why that sprung up to be more common here in a little bit. And then the last phase is going to be, I guess that we can draw a box here. So this is validation. And then evolution is just keeping the notion that the software is probably inherently flexible and is going to change. The requirements that our customers have come up with are probably going to change due to business circumstances, like maybe the meme base becomes massively successful and the customers say, well, now we need to have these new features where we're going to integrate with social media and we'll have postings on LinkedIn and we're going to have this Reddit thing. I don't know. Maybe we'll let you have clicks on meme base so you can make like a meme page for a school. I don't know. But these requirements can evolve and change over time, and then our customers might come back to us and say, well, hey, we'll pay you to improve your system so it now meets our new requirements. So while there's maybe historically been kind of a demarcation between development and evolution, this is becoming increasingly irrelevant as fewer and fewer systems are completely new. Like everything is built off of something else. Everything is full of modules from something else or reused code. There are huge amounts of churn in the functionality of widely used systems. If you think about like Facebook and how often that code changes, we're going to look at how they do that. But Facebook's website, I honestly, this stat is now a few years old, so I'm sure that it's much more frequent, but they used to at least update it at least twice a day. You would be updating the code on the site. That's like crazy, right? We're adding new features literally multiple times a day. So we want to try to make this whole process at this high level picture. I guess that we put something here also because of evolution. We want to make this as painless as possible. So if we say that building software is going to consist of these 4 steps, specification, design and implementation, validation, and evolution, how should we structure our organization and development teams and tasks to do this most efficiently? So we're going to look at a few different classical and then more recent process models for how these different phases get laid out. So the first and simplest is the waterfall software model. The waterfall model is pretty widely used today, and you can see what happens in it, right? So we start off in this requirements phase, and then we move into the design phase, and then we move into the implementation phase. After we do our requirements, we're going to validate them and see that they make sense. After we make our design, we're going to verify that the design matches those requirements, and we already validated that those requirements are what the consumer wanted, what the customer wanted. Then we'll build our implementation, and we're going to test the implementation to say, well, does this implementation seem to implement what we design? And then after it's implemented, we're going to move on to operations, it's going to run, and eventually we're going to discontinue it. So the waterfall model is pretty widely used today. It's got some advantages and disadvantages. So one key advantage is that in the waterfall model, there's measurable progress. We can tell where we were yesterday versus today because we're in the requirements phase, the design phase, or the implementation phase. I can say, well, I expect that in 3 weeks I will be done with the requirements, and then I can move on to design and so on and so forth. We might be able to apply experience from prior work where we were familiar with saying, well, it took about 2 weeks to come up with the requirements last time, that maybe it'll take about 2 weeks to come up with the requirements this time. And you might end up producing artifacts that can be reused in other projects along the way, but it's not necessarily going to be a key component of the design. What are the disadvantages to the waterfall model? Well, it's a waterfall, right? I start off in requirements, and then I move into design, and then implementation. What happens if I did my requirements gathering, and then I start doing my design, and then I start doing my implementation, and then the customer comes back to me and says, oh, by the way, that requirement, it turns out there's one more. You're kind of stuck. So in the waterfall model, it's really pretty difficult or impossible to accommodate change after the progress is underway. In a waterfall model, you only move forward to the next phase when you're done, so you can't really backtrack. So perhaps the opposite of the waterfall model is you could say, well, what if we just made this kind of a cycle and we'll allow backtracking? So this is where we get agile. This is maybe the first buzzword of this buzzword-filled lecture. So in an agile model, we have an iterative process where we build several iterations. Each iteration is a few weeks long, and each iteration is going to consist of just a few features. So an iteration consists of the entire cycle that you might otherwise have in the waterfall, right? You've got your requirements, you've got design and implementation, you've got acceptance and delivery, and you've got operations. But then you see there's a loop. Then you go to next, and you go back, and you go through this, and then you go through it, and you go through it, and you go through it, and you go through it. So the idea is that probably requirements are always going to evolve as you're trying to build something, so you might as well just kind of bake that into your process and say, well, I assume requirements are going to change, and we will evolve as they do. Plus, it turns out you can probably get some useful feedback by delivering a partial application. So how does this play out? Let's see what this iteration might look like. So we'll start out and we'll get all of our requirements from the customers. We've got that users can generate memes, and we've got that maybe it's 1A and 1B and 2 and 2A. So I just broke these down so that we've got these high-level requirements. This is one high-level requirement, and this is another high-level requirement. So in the waterfall model, we would gather all of these requirements, and then we would design this whole system, then we'd implement this whole system, then we'd go back and see if this whole system meets what the customers want. In an agile kind of model, instead, we're going to break this into components, into iterations or sprints, depending on exactly what kind of agile model we follow. We might use a different term, but they're different iterations. So in this case, it might be make sense that we could say that we have 2 iterations. I have iteration 1 here, where users can generate memes, and I have iteration 2, where also users can create meme templates. So then we'd go off and we'd talk to our customers, and we'd find out all of the requirements just for generating memes. Yes, you can tell me all about the template stuff, but I'm not going to do it right now. We're going to design and implement the system just for generating memes, assume that users can't generate these template things, they just already exist. Then we're going to try that, we're going to see if it works, we're going to start building this out, and we'll have people using it. And then once that gets out in the field, we'll start developing the next feature, basically. So this might let us get useful feedback because we'll be delivering part of it early and we can see how it works, and also be a little bit more evolutionary when it comes to changes in the requirements, because if then later on our customers say, oh, now that we see how you generate memes, we really want to change this whole template thing. In a waterfall process, you say, well, that's tough because we already locked it in. But now it hasn't happened yet, so you can easily evolve it before you build it. So this gets us to the first of the continuous buzzwords that we're going to talk about today. We're going to talk a little bit about continuous development. So continuous development is a lot like Agile, but with Agile, we might have lots of developers who are all working together on the same iteration or the same features. But in continuous development, we might be always having different teams working on different features, and then have some formal mechanism for deploying new versions of that code and validating them. We have production-like kinds of approaches so that we can maybe try things out at a bigger scale than just testing them ourselves before we give them to all of the users. So we call this a staging environment. So where does a staging environment come from, and what do we use it for? As software gets more complex and we have lots more dependencies within our software and between it and different libraries and different modules, it becomes kind of impossible to simulate the whole thing just when testing it. Like to try to use one little component, I'm building just my one feature and I want to see if my one feature works, you kind of have to try the entire system all at once. So the idea is that rather than deploying it straight into production and having users using it and finding like bugs in it all over, or just having it testing it on our local machines, we have a kind of production-like environment that not everyone uses. But it looks like production, and it has all of the same kinds of features and goals as the system that is in production that all of our users are really using. 2 examples of how you might use a staging environment. The first is, it's called dog fooding, or eat your own dog food. So this is the notion that if you are building a product, then you should be using that product. And if you are building the bleeding edge development version of that product, you should be using that bleeding edge development version of that product. So for instance, engineers at Facebook all are forced to use this staging version of Facebook that has all of the newest features that aren't yet deployed out to everyone, and that's because they're just making sure that it's stable. Other platforms might have like a formal alpha or beta tester program where users can opt in and say, I would like to get early access to see new features, and I'll give you my feedback, and I understand that maybe it'll be broken, and that's okay. So staging environments are great because we're going to be building all of these new features, and we're not sure if they're going to work, and there's a lot less risk if we see a problem that occurs in the staging environment than in production. So when we have these three environments, the testing, staging, and production, we might have developers who have their own little testing environments, and then we're going to develop new features, and when those features seem good, we promote it towards production, which means putting it in some staging environment, which is where we might have beta testers or we might have dog fooding. Our testing environment was maybe just like our local machine, but our staging environment is going to consist of a few servers that replicate things so it looks like production. Maybe I have a database server, so I have a staging database server, and all of these things there too. And then after things stabilize in this staging environment, it looks like a feature is going to be okay, then we push that out towards production, and it is what's going to actually start servicing like our users. So whose job is it to decide that these changes can get promoted, that it worked in my testing environment, so now it can go into staging, and then maybe it worked in staging and it goes into production? Someone has to be monitoring this. So maybe a technical term here would be operational responsibility. So when we deploy things, we need to have someone whose job it is to monitor it, to make sure it's working okay, to make sure there are no bugs and so on and so forth, between these three environments: testing, staging, and production. So in the waterfall model, it's easy. We have specific staff whose job it is simply to monitor all of the software and set up these testing, staging, and production environments. We may not even have staging because of how backwards we are. And if I'm a developer, it's not my problem. I will develop a feature, and if the feature looks like it works to me, then I will push on it, and if it breaks when it's running, someone else has to figure out why it broke. In an agile model, developers are all going to be doing their testing locally, but we still have these separate staff who are in charge of making sure that the staging and production environments are working and that features are looking good there. So here's ding ding, the next buzzword for this lecture is DevOps. So what is DevOps? DevOps is when developers are going to take ownership of features that are in this staging environment. So if I write some code, I test it myself, it's my problem if my code doesn't work when I test it myself. It's also my problem if I say this looks like it works, deploy this to staging, and then it gets to staging and it doesn't work. It is the developer's responsibility to monitor it and check it. We might still have operators who are paid specifically to monitor the production environment. There might be fewer of them, and we might also have developers who are working really closely with that. So what is DevOps? DevOps is a notion that developers should be responsible for their code all the way through. I write it, and then we make sure that it works. What are the values of DevOps? In DevOps, we say that there are no silos, walls, or responsibility pipelines. There's no finger pointing to say whose fault is this bug and who's responsible for fixing it. The person who wrote it is in charge of that. In DevOps, you have one team that owns any change, any feature, any bug fix. They say from cradle to grave. So from the time that a new feature is conceived to the time that that feature is retired and removed from the product, you have one team who's in charge of that, and hopefully not that much turnover, so you have the same engineers who started on that team, finish on that team. Your team is the support person responsible for those changes regardless of the platform. So here's an example pulled from the Facebook post that I linked to on the start of this lecture. So this is when Facebook first started building mobile products, what their teams looked like. So Facebook had their traditional, what did they have first? Just desktop and web. So they had a desktop and web app product, desktop web product. And then for that product, they had several different engineering teams. They had one team whose job was messages, they had one team whose job was events, and they had one team whose job was photos. If you had something at the intersection between these two products, these two features, you'd maybe have the teams collaborating, but there was clear ownership. And then after they made the website, they decided, hey, we should probably have Android app and iOS app too. And to do that, at the time when they wrote these apps, Facebook decided to have these platform experts. So you can see that for the desktop and web, they have a messages team, they have an events team, and they have a photos team. And then for Android, they had an Android team, and for iOS, they had an iOS team. So these were teams whose responsibility was the platform, which was Android or iOS, but not the product and not the features. And what ended up happening here was then, of course, you have this huge mayhem because you want to have consistency across platforms, right? Group messages on the desktop, why would that have different features than group messages on Android? And why would that have different features from group messages on iOS? You can have a lot of finger pointing here, right? So there's a bug in group messages on Android. Is that because the Android team did something wrong or because the regular messages team did something wrong? So that was not DevOps. So this is what it looks like now in Facebook. This is DevOps. This comes closer at least to matching these values here. So rather than having an Android team and an iOS team, everything is segregated simply by feature. If you're a developer for the chat team, you're doing chat on every single platform, and you are an expert for that product, and you're responsible for that. We're going to throw a few more continuous X buzzwords on here too. So we saw continuous development. Continuous integration is going to be the practice where developers will be automatically building, testing, and analyzing each software change in response to every software change committed to the source repository. So if we're now in this big company and I've got a whole lot of developers, I'm going to have lots of different code changes, right? I've got lots of developers. Maybe let's just say that I've got 2, and I've got some code base. And developer 1 might make some commit here, and developer 2 might make some commit here, and then developer 1 might make some commit here. So this is like version 1, version 2, version 3. So with continuous integration, all of the changes that each developer is making are going to be constantly integrated into the same code base, right? So we can see I've got this one line here which represents what the code is, and each developer's changes are being like reflected right away. What is the difference between this and not continuous integration? So this is maybe continuous integration. What's not CI? Not CI is going to be I've got my 2 developers and I've got my code, and then this developer has a branch and this developer has a branch, and this developer is going to make a change, and this one's going to make a change, and then this one's going to make their other change. So what happened here is I've got these branches, and each developer is working in their own branch. And because of that, they are not sharing these commits between each other, and they're not integrating those changes. Here in the CI picture, we can see all of these changes are being shared and integrated immediately. We'll talk more about continuous integration in a moment. Continuous delivery is a practice that ensures that each software change can be delivered and ready for use by a customer by testing it in these production-like environments. So this is creating these staging environments and constantly pushing these changes into that staging environment. So maybe we'll cherry pick stuff and say, aha, now at this point, deploy to staging. And having some regular cycle for doing this. And the last continuous thing that we're going to talk about is continuous deployment, which is going to be the practice where these incremental changes are going to, in addition to being deployed to staging, eventually we're going to say to production too. So how does continuous integration work? In continuous integration, we have developers who are going to be constantly checking code into some repository. So we've got that in this picture here. We have this one repository and all of our code is constantly being checked in. But in addition to just being like in the same repository together, we're actually going to try to do something to automatically check it and make sure, yes, yes, no, this one is wrong, something is wrong here. So to do this, we have this build robot that every time we send a new version of our code to our version control repository, it's going to do some automated checks and notify the team if there's a problem. What are the principles behind continuous integration? The idea behind continuous integration is that we're going to be committing this code frequently. So in our picture here, we see that each time the developer makes a change, they share that code and they commit it so that other developers can see it. They're not committing broken code because they're sharing it with the other developers and we don't want them to be like dealing with our mistakes. If we get to this point where our automated checks say this is bad, that needs to be fixed immediately because these checks failing, now what's going to happen if we want to introduce v4? I don't know, because we know that it was broken in version 3, so can we keep moving to version 4? Probably not. We need to fix things here to get them working again. We need to have some automated tooling that's going to make sure that these automated checks will actually run and happen. We're going to have tests and inspections and make sure that they all pass. Developers probably are going to be, whatever these checks are that are happening on the server, it would be pretty embarrassing if you didn't also do these checks locally, right? So before I do this commit, I want to check it and make sure it works. Before I do that commit, I want to check it and make sure it works. Check it and make sure it works. If I'm going to make a commit and I see it doesn't work, I should probably not make that commit because otherwise I know it's just going to break things later on. So once we have this integration pipeline, we want to take this and start actually getting that out there in the field. We're pushing that maybe first into staging and then into production. So we have this pipeline of taking our code, developing it, and checking it. So it starts off with doing our local development. That's going to be where our developer is writing their code and maybe sees if checks work or not. If all of those checks pass, they're going to commit it to version control, which is going to allow it to be integrated with other changes coming from other developers. We'll have this automated building and running those tests in our integration platform. We might then automatically take if these checks pass, take that code and deploy it to a staging environment, monitor in that staging environment, eventually deploy it to production, and then monitor it there to see that it works too. So how fast does this work? And how do we decide that at some point, hey, this is a fine revision that I can start pushing into staging or pushing into production? We end up having this pipeline that has some latency, right? There are a lot of steps here. So a feature that I develop right away might not be released right away. But a feature that you develop right away is probably going to begin this release pipeline right away that will start moving through the local testing, the staging, and the production environments. So pretty much any company that's following some form of DevOps or continuous integration or continuous deployment has someone either whose entire job is this release engineer or who's also a developer and happens to be the one who's this holds these keys to be this release engineer. So the release engineer is an individual who acts like a gatekeeper and is going to decide when something is ready to go out or not and oversees the actual deployment process, like the physical or logical process of taking the code, having it running and staging, and then making sure that it works, and then it going into production. The release engineer is not going to be responsible for fixing something that's broken, but they're responsible for being the one to say, hey, Bob, you broke this. You need to fix this. Or maybe, if necessary, going back to the business users and saying, the customers, and saying, hey, I know that we wanted to get this new feature out, but you cannot put this out today. It will not happen. Let's look at an example of what this pipeline looks like and what the release engineer's job is working on Facebook.com. So with Facebook, again, this information is maybe a few years old, so I can't attest that it's entirely up to date, but it's a pretty nice representation of a good model at least. All of our developers are going to be working in their own code branch in version control. So they've got the code for the platform for the product on their computer, and they'll be developing it, and they're going to maybe have lots of commits. And when a feature is ready, the developer says, I'm ready for this feature to start moving into this pipeline and start getting towards being released. They take all of those changes, squash them into a single commit, and push that change into Facebook's master branch. This is the one that all of the developers are pushing their code into. That's going to be doing this integration. And then after about a week, all of the changes that have been sitting in this master branch and haven't caused a problem are going to go into this stabilizing mode, where for a few days, they'll be running in the staging environment, and we'll see if there are any problems detected or not. And how do you detect a problem? I don't know. We'll see it in a second, though. And then if they survive these first 3 days of stabilizing, they're going to sit around for a little bit while longer in the staging environment, but in a release branch. And the release branch contains the features that they started off in the blue, right? Developers worked on them, they tested them, they worked fine for the developers. Then they were pushed into this master branch, and they survived for about a week there. And then they survived for at least 3 days in the staging environment with no problems happening. So they are ready to be released. But not every feature gets released right away. Facebook has its production environment, and then twice a day, changes get pushed from the release branch into the production environment. So you don't take all of the changes that are sitting in this staging environment at once and send them into production, but you do it a little bit more gradually. This allows for maybe a little bit more finer grained detection of if one specific change caused the whole system to break, it'll be easier to detect because there are less changes going in at once. How do you decide that something is ready to go? Well, it's ready to go if it survived all of these steps, and you're sitting there at your desk the entire day that your feature is scheduled to be released, because if it does not work, you need to be able to answer your phone immediately to describe why and how you can fix it or how you can back it out. And the default is, when in doubt, back it out. So if you get to a point where you think that some feature might be ready, but then there are some indications that it's not ready, the answer is it's not ready by default, and you need to prove that it is ready. And then the whole time that this is happening, it's a cycle, right? So developers are constantly working in their own branch, and after these features first were in this 1 week branch, you have some stuff in staging and then more stuff getting pushed into the master branch. So this is the high level model used for Facebook.com, not for mobile. So we have these thousands of changes potentially coming together at once in this staging branch. And we want to have some way that we can isolate individual problems. Each change that we're adding might potentially be causing a problem. So each change is independently integrated and tested with the entire system, which means that Facebook does, again, years old, 20 to 30,000 complete integrations per day just for their mobile apps. So that's taking their entire code base, adding another revision to it, and running all of the tests for it to see if it works, tens of thousands of times a day. And this might seem like it's really expensive, right? This is maybe a lot of CPU hours. You have thousands of servers somewhere in the cloud. I guess we're Facebook, so we have thousands of servers easily. But it's going to cost money to have these computers running, burning CPU cycles. But it turns out that a pretty good general rule of thumb is that the amount of time it takes to run the tests is usually way less than having the cost of a failure. So you're better off spending all this extra money up front doing the testing than not doing the testing and then having some potentially catastrophic failure. So what are other kinds of models that we can look at? So one is blue-green deployment. This is, again, something buzzword worthy. In a blue-green deployment, we always have two complete environments ready. The one that we're using right now in production that has our app that's servicing user requests, and then also one that we're just about ready to use. And then we have some easy way to switch so that we can handle requests in a different one. So literally, our production environment just is split in two. Well, I shouldn't say AB because that's something else. We'll say blue. And then we'll have all of our users and all of the traffic goes to one, and then we have an easy way to make it so that all the traffic goes to the other instead. So a blue-green deployment system is very useful just in general for rolling out updates because I can have all of my router, sorry. All of the requests are being sent to the blue one, and then we want to have a new version of our code, right? So this is version 1. Maybe I'm going to put version 2 over here, and then when I think that I've got my version 2 already, I'm going to take that and we'll send it over to the new one. And this can be maybe a little bit more seamless than having to take the system offline to upgrade it. So something that's really related, if we have this mechanism set up already where I can have multiple versions of my code running and some way to pick which users see which version of the code, is we could do A/B testing. So with A/B testing, we might test new features for usability or popularity or performance by simply changing which version of the code some users see. So I might have two users here. I've got one user making black requests and one user making blue requests. And I might take this user's requests and send them to a different version of the code. So I'll show half of my site, half of my users will see version A, half of them will see version B. I might collect metrics on each and decide which is better. So metrics might mean things like how long people spend on the site or how much they click on things, or if I'm making a store, if I'm Amazon, I might look at how much people buy in terms of sales. Maybe it turns out that putting stuff on the page in a different place will make me more money. We can test that stuff. What other kinds of stuff can we monitor? If I am more in the DevOps side and I want to see that a feature is functional or is full of bugs, we can monitor a lot of very generic stuff. For our hardware, we can monitor things like voltage of the CPU and memory and temperature and fan speeds and component health. This is not likely to be very directly affected by the changes our code makes, but it could be indirectly affected. If nothing else, you might, catch that now all of a sudden you're accessing disk a lot more than you used to, and it wasn't a performance problem, but it's something that you're noticing because it's causing something to overheat. Who knows? Can measure at the OS level things like how much memory is being used, if you're using virtual memory, how much disk space is being used, how much of your CPU is being used. You can still have pretty generic stuff in the middleware layer. So this would be, for us, maybe we're talking about Express or Firebase. So look at how much memory is free for Express to use, or how many connections Express is making, or how long it takes on average for a response to be generated. These are still really generic, right? I don't need to have specialized code written just for whatever the application is that I'm running in order to detect that something is wrong here. We can just do this generically. For all Express applications, you can easily measure how long each response takes to generate. And then in our applications itself, we might be monitoring things that are more domain specific to what we're doing, like how many transactions we're making, the conversion rate. So if someone visits our app, how long do they spend on the app, or the status of some third-party components like libraries that we're using. In a DevOps environment, when things go wrong, it's pretty important that we have some automated monitoring system to automatically notify some on-call staff of a problem. So this kind of system might be smart enough to recognize that a feature is responsible by some team and automatically notify that team, or you just have some on-call staff and say it goes to them and then it gets triaged. But we always have some sort of a triage and escalation process. Especially if this is something that's happening in a production environment, you might have a system like immediately after we're running low on memory, notify whoever's on call for that time, and you might have some schedule to say who's on call. If after 15 minutes it's still a problem, then also notify someone else. If after 15 minutes it's still a problem, then also notify like everybody's boss who's gonna figure out what's going on. In DevOps environments, dashboards are also can be really critical for allowing operators to notice and detect when there are issues, just because even if we can automatically detect some stuff, other issues might not cross like a threshold, but might be something that we would notice just by looking at it and say that's kind of interesting. Like on this load graph here, we can see for the CPU load on some machine, maybe 3 is what this number here, 3 is what our alert is at, so we never hit 3, but we happen to notice from looking at this graph, there's kind of this interesting trend here that there's a wave, and we want to understand more maybe why that wave occurs, and is that because our software has some performance issue that happens at some times of the day, or are more people using our system at some times of the day? Not sure, but something that could be worthwhile to look into. There are lots of different systems that will generate these dashboards for you. Nagios is one that's still very popular, and many other systems that are less free than Nagios are based on Nagios. Last high-level DevOps kind of topic might be canaries. So canaries allow us, when we do this multiple deployment here, where we have a blue version and green version, or A version and B version, or old version and new version, to monitor both of them, right? So we're going to take the requests that we're getting, and we're going to send most of them to the old version, but some of them are going to go to the new version. So that maybe only, say, 5% of users are seeing the new version. So this is a canary in that, well, we all know the canary in the coal mine one, right? So this is something that's going to warn us ahead of time before we have some massive problem, like an entire mine collapsing over our heads or running out of oxygen. So we'll take some small number of the users, send them to the new version of the app, and then we'll start to see how the new version of the app behaves. Maybe we have our load graph that shows how busy, how overloaded our CPU is, and when we start having just 5% of the users come in, it might look like this, and this is like 100%. And if we see this happening with only 5% of the users, we're going to say, oh my, we should probably not be sending more traffic to this new version of the app because it has some performance bug in it. And these performance bugs would be a lot more problematic if we had 100% of the users using it. This was load, right? But by having just some users start using this new version, we're able to see these bugs without impacting so many users. We're minimizing the impact of those problems. So how do we make it happen? If we want to be doing great deployment processes and this whole software process thing, we need some tools. I said this wasn't going to be a tools lecture, but we're going to talk about maybe some classes of tools before we wrap up. So that's going to be build tools, test automation tools, build servers, and deployment tools. So build tools. we need to have some way to automatically construct our executable software. Like, to run our application, we might have to say, well, install this project, this module D3, also this module Bower, also this module Grunt, and do this using npm. And because I'm on a Mac and npm might not be installed, I'll say install npm using Homebrew. So we want to have some general method for describing and executing these build tasks, which might include things like minifying your code or analyzing it in some way, or running tests or generating documentation, and even doing this actual deployment of saying take your code and send it into some staging environment. And we want to do this all in a way that's repeatable, reproducible, and standard. So there are all different kinds of tools to help us do builds. You can get pretty far just using npm and scripts. You've already seen npm pack and npm run start and npm, I think that we have deploy with create react app that's going to generate that, do this generation actually, right? It'll do the minification of your code, it'll take all the React libraries and it'll put them together, and it'll remove the parts that aren't used, and it's going to make them as small as possible, and all this stuff in an automated fashion. In the old days, we might just look at things like makefiles. If you're in Java, you might be looking at Gradle or Bazel or Maven or Ant, all different kinds of build tools. And then once we have the standard mechanism for describing how to build the code, there's not really any reason why we need to do it all ourselves. We could use a build server. So if we're doing this continuous integration thing, that we have something that's automatically doing this testing for each commit, we want to have a continuous integration server that's going to run these builds in the cloud. And examples of these systems might be Hudson, or Jenkins, or Bamboo, or Travis, or Circle CI, there's a whole bunch here. These systems are designed to be super easy to use, to just basically monitor your source repository for changes, and then when they see a change in your source repository, they will run the build. This really helps with organizing tests and results, because for each version of your code, you will have a build, and then for each build, you'll know which test passed and failed, which is really nice. And then, because this is a separate system, of course, you can scale this thing independently of the rest of your process. So you might have 100 developers and only one build server, and then it turns out that you need more build servers or less build servers, and this is just something that you can add separately. So Travis CI integrates directly with GitHub. Travis is free for open source projects, so if you guys want to try it out, it should be pretty easy. The way that it works is when you commit code to GitHub, Travis CI automatically gets notified that you made a new commit, and then it's going to run whatever your build script is on each commit. And then it is going to generate this complete history for each branch of your code that it shows which builds passed and failed, and maybe on some branches they're failing more. And on each commit, you can see what exactly happened and get a complete log. So, summary, wrap up from this lecture. We talked about a lot of software process techniques, right? Less code, more the how, the human side. Key buzzwords, we had developers as operators, that was DevOps. We had all of the continuous things, continuous integration, continuous deployment, continuous delivery, those techniques for reducing the latency, the time that it took to get features out the door. We talked about staging environments to help reduce risk, and build systems and services to help automate continuous integration. I would like to remind you the midterm is going to be on Monday. Unfortunately, I'm not going to be able to be in on Monday either, but Professor Latoza has very generously agreed to show up to proctor the exam for you all. Reminder that this material will not be on the midterm, and the security material will not be on the midterm. If you have any questions while I'm away, please feel free to post on Piazza, and I will do my very best to answer as quickly as possible, and if needed, we can set up a video call or anything for more complicated questions that you want to discuss in person, but again, my apologies for not being there. Thank you.